start by just remembering the scalar equation of a plane and practicing going through all the different versions of equations throughout this, like going back and forth from one to the next kind of thing. So this is a scalar equation of a plane, and to remind us the visual, we're going to do some different kinds of visualizing today. So if we call this plane pi, I got lots of direction vectors within this plane. Okay, infinite number, and they go all different directions. So one direction vector parallel to the plane. We don't call direction vectors in the plane. You can think of them kind of like that, but be careful because they're not in the plane. They're parallel to the plane. But that's because vectors don't exist in a particular position, but they help us define the orientation of the plane. But even better is the normal, because a single normal tells us more about the plane than a single direction vector. That's why it's useful. And there's only one normal to the plane and scalar multiples of that normal. When I say one normal, you can scale it up, scale it down, whatever, but you can think of that as like a family of vectors. Okay? And we remember that the normal from scalar is really easy because it's coefficients of x, y, and z. We could also have points in the plane. We're going to look at that. And points, I suppose, not in the plane. Okay. Given normal vector of a plane and a point in the plane, find the scalar equation. We did this yesterday. What do we do? The learning goal just said find the equation. It didn't tell you which form, so you could do whichever one you want, depending on what you think of and what you find first, I guess. Seema? So I think that's a good start. This is how we did it yesterday. 2x plus 3y plus 1z. And people forget this. Plus d equals 0. That's the part that people forget. And they just leave the d out, so d is 0. Or for some reason, somehow, some people make up a d. I'm not sure how that works. Maybe you find the magnitude or something, or I don't know. But okay, but you write it d, and then we use our point that we're given, 425, and sub in and solve for d. Don't forget to write the equation. This is another thing that people forget. Okay. Yesterday, I talked about using GeoGebra to visualize this stuff, and I was playing around with it, and we noticed that the URL is pretty easy. So geogebra.org/3D, couldn't be easier. Takes us to where we want to be. 3D calculator. Okay. And I'm going to try to adjust my window size here a little bit so that it's properly on the screen. Give it a second here to apparently load. And there you have it. And you can type things in like 3 plus 4, and it gives you 7. Like you can actually use it as a calculator. Not a great one if you have a calculator lying around, but you can use it. But if you hit this, this is the geometry tools button, and all of a sudden you have some tools here. But I'm going to go back here, and we can also, you can type in this, obviously, like I just did, but you can also, scalar is actually really easy to input. So 2x plus 3y plus 5 minus 19 equals 0. And bam, we got a plane. Did I type that right? I did. Okay, and you can visualize it. And I think that's a good thing for you to be doing. Okay. Whoops. Ha, our comic. Okay. Let's do some other things. Is Q on the plane? How are we going to do that? Seema again. Left side equals right side. So this is a useful to have scalar form for this. So we're going to check for -1, 2. Left side is 2 times 4. 3 times -1 plus z, which is 2. Oh, I did type it in wrong. That's why. Yeah, I'm gonna have to go back and fix that. And because I wrote it wrong. Did anybody catch that? This should be z, right? Instead of 5. Yeah. Okay. And not equal 0. I did that this morning too. And this works out to -12, which does not equal the right side. Therefore, Q is not in the plane. If you had a vector form and you were told to check, you'd be like, oh, I don't know how to do that. And you'd start trying different things and it would probably take you a long time because it'd be hard to check. So you want to know, like, so, you know, I've set this up to walk us through it because you already have scalar and you only have scalar. What if I gave you vector form and I said, check if this point is in the plane? And you didn't know that you're supposed to put it in scalar form to do that. Those are the kinds of things that people have a hard time with. So going back here, what if I type in this point? So again, you can use this if you're playing with this and you want some tutorials on how to type in the things we need to type in. You can come back and watch this part of the video to see how you type. But to type a point, you just type a point with brackets, -1 and 2. And I'm going to go fix this. Plus Z. There we go. And not in the plane. Right? It's just a point somewhere else in space. Okay, what else? Is the vector A parallel to the plane? How are we going to do this? Very good. I think that's the best approach. Sometimes what people think is they're like, oh, well, what if we get the vector equation? Because the vector equation has direction vectors parallel to the plane. But there are an infinite number of direction vectors parallel to the plane. So how does having one more, like what's that going to do for us? Nothing. It's not going to do anything for us. If we came up with the vector equation of the plane, it would be unlikely that that would be one of our direction vectors. It would be a total fluke that happened to work out to be one of them. And you'd be like, oh yeah, so there you go. So that wouldn't work. So this is where the normal is often more useful to do this kind of stuff. So if we dot, we're going to check A dot N. Check the dot product with the normal, because the normal is perpendicular to all vectors parallel to the plane because it's perpendicular to the plane. So any vector that's parallel to the plane, parallel to the plane, yes, will be perpendicular to the normal. So this is always a useful thing to do. So this works out to 1 times 2 plus 2 times 3 plus -3 times 1, which equals 5, not 0. Therefore, A is not parallel to the plane. And this is kind of interesting. I mean, I see people confusing these ideas. We were asked about something being parallel, but our check had to do with being perpendicular, right? Because that's what the dot product tells us. But then our conclusion is back about being parallel, because that's what we were asked about. People can get themselves mixed up in what that is showing. And they say, yes, it is perpendicular or something. So make sure you understand how the normal is perpendicular, therefore vectors are parallel to the plane, or not in this case. Again, what does that look like? So interestingly, if I just pick some other lowercase value, and I don't know why this works, there's different ways you can type things in, and you'll only ever remember if you use it often. I've used this program a lot over the last few years, so I tend to remember the little quirks of it. Other programs are different. But it turns out if I type in b equals and then type in the vector, so it was 1, 2, -3, that makes it a vector. I don't know why. There's another way that you can do it. I'll show you that other way later. And so it's not all the way convincing, but they don't look parallel to me either. We calculated that they don't look parallel. What do you think? Whoa. Find another vector that is normal to the plane. How are we going to do that? See me again. Dot what? With A. A is not parallel to the plane, though. Oh, with N. If I found a vector who had a dot product with N that was 0, it would be perpendicular to N, parallel to the plane. We want another one that's normal to the plane, so perpendicular to the plane. You could do that. That will be a little bit tricky. Yeah, we're just going to scale it up, scale it down, something like that. So if N, our normal was 2, 3, 1, then I could do -2, -3, -1, or 4, 6, 2, ... Not very interesting, I know, but it's just a reminder, and it's what you should know with confidence. All normals to the plane will be scalar multiples of each other. Any vector that's normal to the plane will be a scalar multiple of each other. So this is the only way to find other ones. Well, it's not the only way to find them, but this is what you would do. Okay, even if you did it another way, you'd find something that's a scalar multiple of that. Okay, example 2. This time we're given the equation of a plane in scalar form and asked to find the normal. How do I do that? Yeah. Wouldn't you say that? So what is our normal then? 302. So again, it's in scalar form, so it's just the coefficients, but we don't have a y term, so it's 0. Okay, good. Again, test won't necessarily walk you through all these things, but there's a good chance you'll need the normal to do the things you're required to do. It won't say find the normal, but you'll just have to know that you should find the normal. The lesson's walking us through it a little bit more, holding our hand along the way. Find a vector that is parallel to the plane. How do we do that? Parallel to the plane. Anybody else have an idea? Vang, you got an idea? Yeah, and we have a trick for that. Remember when we learned that in the last unit? There was a reason why we did that and practiced it over and over and over again. We can use our trick. So parallel to the plane means dot product with n equals 0. That's what parallel means. So n is 302. we do it like this, 3, 0, 2. And that has to equal, I'm going to write over here, equal 0. What is usually our trick? Set 1 to 0. But in this case, we already have a 0. So we don't need to do that. I can put in, if I put in -2 here and 3 here, I've got -6 and 6. I can put whatever I want in there. How about a 1? I could also make it 0. So therefore, -2, 1, 3. Or -2, 5, 3. Or 2 pi, I don't know why you would do that, but -3, I think would work as well. You should be able to come up with many, many, many quickly. Again, this is not a question you want to spend a lot of time on. They're parallel to the plane, so they're direction vectors. That can be a useful thing to have. Oh, example 3. Okay, this one's a bit different. Given vector form, find a vector that is normal to the plane. Again, the normal vectors are useful, so this is something you're going to probably want to do, but this time we're given vector form, not scalar. Process is likely to be different. What do you think? You could. How would you do that? Ah, good. Yeah. Yeah. So, so in the first period class, somebody said the same thing as you. I'm right. That what about if we had scalar form? And I said, well, how would you get scalar form? And they say, well, you would take the cross product of these two to find a normal vector, put that in to the A, B, and C, then use a point, solve for D, and then you'd have scalar. And I was like, yeah, but we're trying to find the normal. Why would you do the rest of it? You already found the normal. So you're right, putting it in scalar form, but you know, halfway there, you would be done already. So good. So I'm going to take the cross product. I'm going to call these A and B, or actually, I'll call them D1 and D2. And so the normal, or K times the normal, will equal direction vector 1 crossed with direction vector 2, which in this case works out to -4, 6, -2. Therefore, I'm going to choose my normal as 2, -3, 1. Okay? Find a point on the plane. 2, 5, -4. It's funny when this one stumps people. Like, I don't know how to find a point on the plane. But I'm going to show you, first of all, if you only need 1 point, why not make it easy? So it's the point that the given position vector goes to, right? This is a position vector that goes to a point on the plane. So a point on the plane would have to be, 2, 5, -4. Again, using round brackets instead of square brackets because now it's a point. But what is this point in terms of the vector form of the equation? This is something that I sort of was talking around the other day, but I didn't say explicitly, and I wondered if maybe people, if there's a misunderstanding here or a little gap in our understanding of how this works. So I thought we could talk about it now. It's a good time to talk about it. So this is a point where S and T, which are called our parameters, and that's why it's called parametric form. But this is vector form, but we still have parameters. Our parameters are S and T, and this is the point where, for this equation, S and T are 0. But S and T, we call them parameters, and it means you can choose any value you want. So what if I chose S equals 1 and t equals 0. If I needed another point, how would that work? Well, I would get 2 minus 1. So I would get 2 minus 1, which is 1, plus 0, because t is 0. And then 5 plus 0, so 5. And then negative 4 plus 1 times 2, so that's negative 2 plus 0, so negative 2. So that would be another point on the plane. So you can come up with infinite points using vector form by using those parameters that the whole point is you set what they are. You say what you want S and T to be. Does that make sense? I hope so. That's an important idea. Yes? Can you use normal brackets for vectors? No. What do you mean by normal brackets? No, not for a vector. If you're talking about a vector, use square brackets. Why? Yeah. So this is just a convention, and I've said this before. Other people use other conventions. I mean, take a look at our at GeoGebra. It does them vertically and with round brackets. So other people do it other ways. But the lesson here is conventions matter, and notation matters, and context sometimes changes that. So your professors next year may use other notation, and from one class to another, you may use different notation. So you got to learn their quirks and what their demands are. And don't ever go up to them and say, well, my other teacher does it. They don't care. They want you to do it their way. Some people, it'll just be based on context, so they would always want you to just state that something's a vector, and maybe like some people wouldn't care, but you got to know your audience. That's the lesson, right? Who are you speaking to? Anyway. Okay, find a scalar equation of the plane. So again, we've already done this once today, I think. So how would you do this? You would take your normal, put it in for ABC, plus D equals 0, put in your point that we already found, solve for D, restate your equation. I'm going to show you another way, and then you can use either way you want. This way is probably like one line less of writing. Some of you might like it, but it requires a bit of a leap in understanding, I guess, connection to make. To use this trick, you don't need to understand what I'm about to talk about, but some of you might be a bit confused by it. So anyway, you can use whichever one you want. You can use the one that we did up here, if I can find it. Right there, solve for D, restate the equation, 1, 2, 3, 4 lines. Or you can choose to use this trick after we've done it. So this trick requires that we draw a plane. And we've got a point in our plane. I'm going to use the first point, 2, 5, 4. And I'm going to call this point P, 2, 5, negative 4. And I can also come up with I could come up with other points. Like I have another point, but I actually don't want another particular point. I want point Q to be just general, any point in the plane XYZ. Okay? Okay so far? Then what I can do is I can come up with a vector from P to Q, and I'm going to call it a direction vector that's parallel to the plane, because both those points are in the plane, so the direction vector, or the vector between them, will be parallel to the plane. Does that make sense? That's an important idea. Then what has to be true between the relationship of D and N? They have to be perpendicular, so their dot product has to be 0. Is that okay? But what is vector D? It's PQ. So this is the part that you have to understand and know, which subtracting backwards is x minus 2. Every time you use this trick, you don't have to do all this work. This is the explanation on why this trick works. y minus 5, and z minus negative 4. So we don't want a particular vector, we want a general vector. This is a vector from P to any point and all points in the plane. Does that make sense? When I dot it with n, and n is 2, negative 3, 1, so 2, negative 3, 1, dotted with x minus 2, y minus 5, z plus 4. That will equal 0. And what will that look like? That'll look like 2 times x minus 2 minus 3 times y minus 5 plus 1 times z plus 4. And that has to equal 0. So there was a long process of thinking and sort of doing something new, of thinking about a general point and a general direction vector parallel to the plane to come up with this line. But it gets us a scalar equation. Yep. Yeah. We're going to do this again, and like you can streamline this process further. Yeah. You don't have to do all of this defining work or anything like that. So this ends up being a trick that can get you to scalar quickly. Some of you might like it, some of you might not. As I said, you can use the other way of solving for D. You can decide. All right, let's try. Any questions about that? Try some other things. For the plane, given scalar form, find a vector that is normal to the plane. Hopefully we know how to do this now. Go ahead and do that. We just did this in vector form. Some work was required. Doing it in scalar is easy. Trivial. Find 2 points on the plane. See, this is what we were talking about, right? So make it easy. And we are calling these points A and B. So A will be when y equals 0 and z equals 0. So these are gone, and I get x minus 4 is 0, so x is 4. 0, 0. What about when x is 0 and when z is 0? Call that our B. So 0, 0, and negative 2 equals 4. So y, negative 2y equals 4, sorry, so y equals negative 2. So intercepts. If I set x and y equal to 0, I'd get a fraction for z. Don't do that. Like, again, if you set things equal to 0 and you get a fraction, go back and be smart about it and fix it to make it better, because, and you have an x in here that you can make whatever you want, so you could, that would be easy to work with, to do a bit of a guess and check, but at least try to use 1, 0, because that will make your life a lot easier. Don't use fractions, because then you start doing a cross product with a fraction or something like that. Like, oh, what a disaster that would be. What does this look like? All right, I'm going to get rid of these things for now. going to type in the equation of this plane, x minus 2y plus 3z minus 4 equals 0. That should give us a plane. There it is. If I can orient it, there we go. That's kind of good. Then we got 2 points. We looked at a point not on the plane before. I don't think this is too hard to understand, but what about a point or two that are on the plane? So take a look at that. And they're intercepts, right? So they're actually where the plane crosses the axis, but you can see how they're on the plane, sort of. Yeah? Okay. What else do we have to do? Oh, determine AB. This is just a process that helps us make some connections. We're not like doing a thing necessarily here that's useful, but we're going to show something that we should understand why it's true and that it's true. And finding a couple of points in a direction vector or a vector between them, that's something that could be useful, right? So AB is subtract backwards. So 0 minus 4 is negative 4. Negative 2 minus 0 is negative 2, and 0 minus 0 is 0. And then our next thing to do here is show that AB is perpendicular to N. Does that make sense that it would be? AB is a vector parallel to the plane because it's between 2 points that are in the plane. So it had better be perpendicular to the normal because the normal is perpendicular to the plane. So all vectors that are parallel to the plane as well. And how am I going to do this? How am I going to show this? Dot product. So negative 4 plus 4, which is 0. No surprise, but that should happen.
So if you multiply the normal by a negative point, like a point, but multiplied by negative 1
Yeah.
on the plane, it will give you D.
Say that again.
Okay, so let's say we have the position vector, right? So negative 1 times the position vector dot normal gives you D.
Gives you D?
Yeah.
Why is that?
I don't know. That's not. I got that.
Okay, let's look at that after. I mean, it might be a fluke that happens in some cases, depending on what things you have, but it might be true. Let me think about it for a second. Well, let's get this done first. Okay, any questions about that? Oh, that's because, I see what you were saying, because of the other process that we did. Yeah. Okay. All right. Plane in parametric form, right in vector form. Again, going back and forth between all the different forms is just something that we need to be good at. How am I going to do this? Yeah. So what is it? So hold on, 2, 1, 6. Which are these values? Right? Just the constants in each of the parametric equations and written in order. Parametric equations should always be written in order, like alphabetically, X, then Y, then Z. If they weren't, be careful. Somebody's trying to trick you, I guess. Good. And then? Plus S. So the parameters are given here. We generally use S and T. Wouldn't necessarily have to, but in this case we are. Good. So the third one doesn't have an S term in it. So again, it's 0. Plus T. Good. Find a vector that is normal to the plane. So we're given parametric. We've got vector form. How do we find a vector that's normal to the plane? I think we kind of already did this today, but what do you think? Daniel, do you know?
You just take like S and then since it's already got a 0 and then you just do like negative one of the numbers.
Be careful, because you can have, this is a good point. You can have vectors parallel to the plane that are perpendicular to each other, right? Let me see if I can find that sketch from the very beginning. Watch.
Right, okay.
So what do we have to add to that? The dot product will find us a vector that is perpendicular to a single vector. Cross these, and we will call them D1 and D2. And remember, that's like going to be our normal, or K times our normal vector. And this works out to 3, -9, 1. So I can't really reduce that in any way. So that'll be our normal. Good? See the difference between the different forms and different ways that you do things and stuff? This is what we need to be good at and we need to know. There's a lot of what the quiz will look like. Find a point on the plane. We did this before, and I'll do it quickly, but reminder, this is the position vector to a point on the plane. Use that one. We only need 1 point. Why not use the one that we already have? So I'll call this P, and it's -2, 1, 6. And find a scalar equation of the plane. So that's what we just did. I'll show you this trick again. So I take my normal, which is 3, -9, and 1, and dot it with, x minus from point P. So x minus the point P, y minus 1, z minus 6. So see how we come up with that? From this point, we did that whole explanation before, and we set that equal to 0. So this is 3x plus 6 minus 9y plus 9 plus z minus 6 equals 0. Six minus 6 equals 9. You got it on your sheet, but those are the recommended questions to do from the practice today.